Hello guys, in this video I'm going to discuss the question 1 for our test number 1. Before I'm going to discuss the question with regard to the question number 1, I would like to recap a couple of things which I found a couple of students are still struggling to understand it. So let us talk about methods. Methods can be in the form of solid, and also in the form of liquid, and also can be in the form of gases. So if I'm going to draw molecules inside the solid, it should look something like this. Meaning that the molecules or the atom inside the solid here was actually quite close to one another. And then for the liquid, most probably the molecules or the atom is a little bit further to one another compared to in the solid. And then for the gases, it even more further together compared to the liquids. So the atom or the molecule here is actually moving between one and another, and then sometimes it will collide between one another. So now let's talk about the water. So the water can also in the form of solid, for example, and ice. And then it is quite common for us to have the water in the form of liquid. And then sometimes we can also have the water in the form of gases. But then we're not going to call the water in the form of gas as gas water. Usually we just simply call it a vapor, or sometimes it is called water vapor, meaning that the vapor represents the water in the form of gases, which is have the same characteristic as the gases. So easiest example for us to understand what does the vapor means or water vapor means, let's say I want to make a cup of hot coffee, and then I'm going to boil a liquid water inside the kettle, and then I'm going to heat up the water inside the kettle. After the water was boiling, you will notice that some water vapor was actually being released from the kettle. So this is what we call a water vapor. It's still actually a water, but then in the form of gases, or we call it a water vapor. Alright. The first part of the question here is actually asking you to construct a TV diagram for the saturation line, the process curve, passing through the initial and intermediate and the final state. So here, they're asking you to draw or to construct T versus V diagrams. So I can say that for this curve, I will say that on the y-axis, I have temperatures in degrees Celsius, and then for the x-axis here, I'm going to have a specific volume with the unit of meter to power of 3 per kilograms. And then this is what we call a saturation line. And then you should get the process curve look something like this. So because in here it mentions that initially the process are constant pressure, so meaning that here the process curve is for pressure equals to 200 kilopascal. So this one should be straightforward. You have to draw a graph look something like this. Yeah, I did found a couple of your friends did draw Oops. Hold on, yeah. A process curve looks something like this, which is wrong. This is conceptually wrong, even theoretically is also wrong. Why? I'm going to discuss why this curve is wrong, yeah? And also for the saturation line here, I already discussed in my previous video on how I obtain the saturation line look something like this. You can refer to that video on how do I get the saturation line look something like this. Alright, so now I'm going to discuss on how to construct the TV diagrams here. So let's say here is my temperatures, degree Celsius versus specific volume in the unit of meter cubes per kg. And then I'm going to just simply draw a saturation line, look something like this. And then I'm going to prove to you how does my TV diagram for the process curve look something like this and not something like this. So here something like this. So this is wrong and then this is correct. So how to prove that one? So we're going to take a look at the simple experiment. So to prove this curve is correct, I will say that I'm going to draw a piston cylinder. This is my piston, and then this is going to be my cylinder. And then my piston over here can either moving up or moving down, depending on the process. And then I'm going to fill my cylinder with water. So here, let's say I'm started with the room temperatures, 25 degrees Celsius. And then I'm going to heat up my water over here. So once I heat up my water over here, you should ask yourself, what happened to the temperatures? Temperatures will be rising or will be increased, obviously, because once you heat up something, the temperature is going to be increased. So once the temperature of the water here increase, let's say from 25 to, let's say, 80 degrees Celsius, what happened to the piston over here? The piston over here, because it was heated, therefore the piston over here is going to be increased. And then once the piston is increased, the volume also going to be increased. Why? The volume of the cylinder over here, cylinder looks something like this, yeah? And then if the volume, I means the here is increased, therefore the volume is also going to be increased. Because why? Because the volume is actually equals to area of the circle, pi d squared over 4 multiplied by the height. So once the piston over here increased to, let's say here, the height, the height over here is also going to be increased, therefore the volume is also going to be increased. Once the volume is increased, specific volume also going to be increased. Why? Because the specific volume is actually equal to volume divided by mass. But then the mass of the water here is not going to be increased because it is a closed system. And then the water is not going to be added from time to time. Therefore, the amount of water is going to be the same. Therefore, the mass is going to be the same. Volume is increased. Therefore, my specific volume is also going to be increased. So this is how I get from here to here. Let's say here as state number 2. Oops. Oh gosh. All right. So I'm going to redraw my piston and cylinder. So now my cylinder looks something like this, and then this is my piston. And then of course this one is a liquid water. let's for the sake of simplification, let's assume that I have 10 liquid water inside my cylinder over here. It's not going to be 9, yeah, but then definitely it's going to be something like 6.023 times 10 to the power of 23 water molecule. But then for the sake of simplification, I'm going to assume that my liquid water inside the piston and cylinder over here is going to be only 10. So now I'm going to heat up. Oops. Oh gosh. Okay. I'm going to heat up my water inside the cylinder over here. And then the temperatures will be rising until one point for which the liquid water here is going to be converted to vapor. So let's name the red one is vapor, yeah, is vapor. And then for the blue one is liquid. So initially I have, oh gosh, initially I have 9 liquid water, and then after I heat up until I reach a certain point, I'm going to have 10 liquid water. Now I'm going to have 9 liquid water plus 1 water vapor. So this is represented by the point number 2 here, meaning that at the point number 2 here, the first liquid water molecule was actually converted to water vapor. So this is what we call saturated liquid. And then I keep on heating up, but then I noticed that my temperatures will remain constant. Why? All the heat energy was actually used to convert from liquid here, see, to convert to vapor. Now as I keep on heating up my water inside the piston cylinder over here, more and more liquid water was actually converted to vapor. So now I'm going to have a mixture of liquid and also vapor until I reach at one point for which the last remaining liquid water is going to be converted to vapor. So this is represented by point number 3, which what we call saturated vapor. And then I continue heating up, but now all my liquid water was actually converted to vapor, no more liquids. But then the temperatures is going to increase because before this the temperatures was remain constant until I reach at the point for which the last liquid water was actually converted to vapor. At that point, what we call a saturated vapor. And then if I'm continue heating, the temperatures will rise, but now I'm going to have a steam. All is going to be converted to steam. So this is how I'm constructed this curve looks something like this. Alright, so I hope that you understand this one, and then of course this one is going to be P is constant, meaning that the process is occurred at the constant pressure, meaning that the pressure most probably due to the atmospheric pressure. There's no weight added to the piston over here, otherwise the pressure will be increased. So now I'm going to erase this one first, so that okay. So now I'm going to construct look something like this, yeah. Let me use raise in. Oh. So let's say the pressure equals to 200 kilopascal. So this is the process curve which look like, yeah. So and again, this one is called a saturated liquid. So if I want to find any information with regards to this point, I'm going to have, let's say I want to find what is my value of VF. So value of V. So the value of specific volume at this point is going to be VF, and then the specific volume at this point is going to be Vg. How about the internal energy? So at this point, let me use writing. At this point, the internal energy is going to be Uf, and then the enthalpy is going to be Hf, and then entropy S is going to be Sf. While for the another point, which is this point, point number 3, my U is going to be Uf, my H, sorry, Ug, my H is going to be Hg, my S is going to be my Sg. And then someone might ask, because from the steam table, I found that so many UF are available, but then we noticed that this process curve is for the 200 kilopascal. Therefore, let's say I want to find the U at this point. So U equals to UF at 200 kilopascal, so that I can use table A5 to find the value of U, most probably in kilojoule per kg. Same goes for the H. So H here is going to be HF, because it is a saturated liquid, which is given condition is at 200 kilopascal. And then I'm going to get the table A5 to find the value of H. Same goes for the point number 3, which is saturated vapor. I can find it by using, instead of UF, but then I have to find Ug at 200 kilopascal, because it does mention in the question that the process occurred at the pressure of 200 kilopascal. So let me label it here. This one is going to be saturated vapor, and then this one is going to be saturated liquid. In between these 2 points, I can find any properties, enthalpy, entropy, internal energy, and etc. from table A4 or A5. Someone may ask, what's the difference between table A4 and A5? If you take a look at the table A4 and A5, you notice that for the table A4 here, the temperature is constant. But then for the table A5 here, the pressure is constant. So in this case, obviously, the pressure is constant. Therefore, I have to use table A5. And also, you should note that here, for this temperature, for the constant temperatures process here to here, from the saturated liquid to the saturated vapor here, the temperature is constant. That temperature is actually equals to saturation temperatures. If I want to find saturation temperatures for this condition, which is 200 kilopascal, I can say that temperatures equals to saturation temperatures at 200 kilopascal. Then I will get the value of the temperatures at 200 kilopascal for which it is a saturation temperatures. And then of course this one, after it was heated, after you exceeded the saturated vapor, the temperatures will rise, and then this is what we call superheated steam. And then for the superheated steam, we have to use table A7, because table A6. So for the table A4 and 5, it is actually for this region. Let me use green. So this region, we have to use table A4 and A5, and then exceeded this region is actually we're going to consider for the superheated steam. And then for in between these 2 points, it is what we call a compressed liquid or compressed water. And then this one is going to be table A7. But then for us, if we're going to study for the chemical engineering, it's very rare for us to encounter the compressed water, because the compressed water here usually are covered by the mechanical engineering student. But then for us, we only have to consider table A4, table A5, and table A6. Table A4 and A5 is for this region. And then for the table A6, it is actually in the superheated region. So yeah, I think I already covered most of it. Let's take a look at the example here. All right. Oh yeah, I forgot to cover on the superheated steam. Yeah. So let me use this one. So I assume that because they are asking for the V diagram, so first I have to show that on my y-axis is going to be temperatures, which is in degrees Celsius. I have to put a temperatures versus degrees Celsius. And then for the V here, for the x-axis here, is going to be specific volume with the unit of meter cube per kg. And then by labeling this point, for the test 1A, I'm going to give you half marks. Make it our life easier. Just label the axis y and also x axis. And then by drawing a saturation line here, not necessary to be perfect as mine, but then as long as you draw a saturation line, then it's going to be another 1 marks. Here, it is going to be 1 marks. And then I haven't covered on the X, yeah, steam quality. All right. I think I have to erase it, some of it first, so that, oh, I can draw it. Okay, let me draw. Oops. Oh gosh. Okay, now I'm going to draw on the new diagrams, yeah. So this is going to be my temperatures, degrees Celsius. This is going to be my specific volume, meter to power of 3 per kg. And then I'm going to draw a saturation line, which is quite important. And then, as I said before, this is actually a compressed liquid. And then this is going to be my saturated liquid. This is going to be my saturated vapor. And then the temperature is going to rise, and then until I reach at the superheated region. So this is going to be my saturation temperatures. So as I said before, for let's say this is my point number 2, this is my point number 3, and then this is point number 4. So for the point number 2 here, any properties, for example, I want to find what is my specific volume at this point. My specific volume is just equals to my VF 200 kilopascal. Same goes for this one. This one is going to be my V at this point number 3. My V is going to be, let's say my V3 equals to VG at 200 kilopascal, because given in the question the pressure is constant at 200 kilopascal. And then someone may ask, how do I get the information in between this line? Meaning that between point 2 and point 3 here. Let's say here is a point X. No, I cannot use X, otherwise it's going to be confusing. Let's name it as a point A. So someone may ask, how do I get the information which is for the process, for the state, which is located in between point 2 and also point number 3. In order for you to find, let's say you want to find what is the specific volume at this point, VA, you need to use X. X definition, it is actually a steam quality. And then the X here is given. The formula for X is actually equals to mass of the vapor divided by mass total, or mass of the vapor, mg, divided by mass of fluid plus mass of vapor. And then from that, I can also use this equation. I can say that specific volume at the point A, which is point A located in between point 2 and point 3, specific volume for the A, for the point A, is actually equals to VF, which is here, plus X, which is a steam quality, multiplied by VFG. Or I can rewrite here as VA equals to VF plus X multiplied by VG minus VF. Why do I use this one? It is because for the specific volume, we don't have a VFG. But let's say I want to find the internal energy, I can also use the same equation, which is, so internal energy, U, at the point A equals to UF plus X UFG. But then the UFG here can be found from table A5. So I don't have to calculate. I also can calculate, meaning that UFG is just equals to UG minus UF. But then you're going to get the same answer as UFG as stated in the STEAM table. So this is how we get the information which is located in between point number 2 and also point number 3. Yeah, I think I already covered most of my simplified note over here. See, I can simplify my notes in one pages only, meaning that all the information I want to find is actually I can put it into one pages, but then you have to understand everything. So the trick of the question here, if you notice that the question here, even though I have so many states, I can either in the form of saturated vapor, sometimes I can also in the form of saturated liquid, and then the question can be started from anywhere. For example, I can say that, okay, I'm started from here. So this is going to be my state number 1, and then I'm going to reach to here. So this is going to be my state number 2. Sometimes I can also have a process which is started from here, and then end up to here, and then end up to here. So this is going to be my state 1. This is going to be my state number 2. This is going to be my state number 3. So many things can be asked. So you have to really understand that. First, you have to identify the state. Which state is actually located? I mean, you know. Oh gosh, I already erased everything. Gosh. No. Oh gosh. Sorry about that. Oh gosh. I can erase everything. I hope that I'll be able to didn't know I can erase everything even though I already saved it so many times. Okay. Alright, now I'm going to take a look at the question, and then I'll try to attempt it so that you have some general ideas on how the question look like, and then how we should attempt to solve for it. Let me erase everything first. I have to erase everything. The question is not going to be the same, but then the good thing about the test 1A here is if you are doing well with your test 1A here, then you're not going to have a problem for the final exam, because this one also being covered in the final exam for question number 1. So I'm going to start here. Alright. So water at 200 kilopascal and 300 degrees Celsius is contained in the piston cylinder. So for this case, usually I'm going to draw a diagram. So I'm going to say that this one is going to be, oh gosh. Okay. So this one is going to be my state 1. State 1. And then I have pressure of 200 kilopascal. And then temperatures of 300 degrees Celsius. And then is contained in a piston cylinder devices fitted with top as shown in figures 1.0. So see, it looks something like this. So this is going to be my state 1. And then it stated that the water is allowed to cool. So this is the keywords here. The water is allowed to cool. Oops. The water is allowed to cool. What does the cool mean? Cools mean that temperatures will be drops, because the cool should be opposites to the heating. So now, at constant pressure until it exists as saturated vapor. So I will say that here is going to be my state number 2, because it is a constant pressure, therefore my pressure is going to be the same, 200 kilopascal. Let me erase this one first. Not enough space, sorry about that. So my pressure here is going to be 200 kilopascal, but then it's going to be saturated vapor. and then the piston rests on stop. So meaning that once it was cool, see, as I explained before, if it was heated, this piston is going to move up. But then it is opposite process of the heating. Therefore, this piston is going to drop until it reach at the pit stop over here. So this is going to be my process number 2 or state number 2. Alright. And then the piston rests at stop. Then the water is continued to cool until the pressure is 100 kilopascal. So meaning that after it reaches the stop here, now my pressure, no more constant pressure, but then the pressure is going to be 100 kilopascal. And then, alright, so I'm going to draw a curve first. Yeah. So now it's going to be temperatures, degrees Celsius, specific volume, meter to power of 3 per kilograms. So now I'm going to draw a process curve. Oops. This is going to be my pressure equals to 200 kilopascal. Alright. Because the pressure is constant over here for the process between state 1 and state 2 here, I can say that this one, T set, is actually equals to, T set is equal to T set at 200 kilopascal, meaning that I can find from the steam table for the table A5 what is the temperatures here. So let's say my temperatures here, I just put a random value, 151 degrees Celsius. So this process occurred at 151 degrees Celsius. But then if you notice that the temperatures here is actually 300. So from the graph itself, you should know that my state 1 is going to be somewhere around here. Why? Because in here, temperatures is 151, but then the temperatures is way higher for the state 1 compared to 151. Therefore, my point 1, my state 1, most probably is going to be here. So if I want to find the information for the state 1 here, I do know that the state 1 here is actually located in superheated. See? Above this point. So it is superheated. Therefore, I have to use table A6. So I can say that my state 1, is superheated region. So I have to use table A6 for pressure equals to 200 kilopascal and temperatures equals to 300 degrees Celsius. Then I can find whatever information I can. I want either it is a U, internal energy, specific volume, enthalpy, and etc. Whatever information I want, because I do know that my state 1 is actually located in the superheated region because the temperatures for the state 1, see, 300 degrees Celsius, which is way above the saturation temperatures for the process at 200 kilopascal. Therefore, I do know that it is going to be my state 1. And then the question does mention that at the state 2 here, I have a saturated vapor. Where does the saturated vapor located? It is located here. So this is going to be my state number 2. So going back to my lecture note over here, see, the point 2 here was actually located here, saturated vapor. Therefore, I should note that my state over 2 here is going to be here. And then this one is a little bit trick here. The piston rests at stop, meaning that my piston here is going to be here for the state number 2. And then the water is continued to cool. What happened if it was cold? Temperatures will be drops until the pressure is 100 kilopascal. So now, because this is the process for 200 kilopascal, so now I have to draw another process for 100 kilopascal. So most probably my graph looks something like this. So my pressure equals to 100 kilopascal. Because this line, this process line is 200 kilopascal. The pressure is constant. But then now I'm going to have new pressure. Therefore, I have to draw another line. Because if you notice that for the TV diagram, T is varies, meaning that T is changed, see, from 0 to, let's say, 200. And then, but then the pressure should be constant, because we cannot have pressure and temperatures varies at the same time. It's difficult for us to illustrate it by using a diagram. All right, so now I'm going to have this diagram, and then I'm going to say that, now I'm going to say that my state number 3 here, state number 3 here is going to be, oh my god, this is going to be my state number 3. So I can say that specific volume at the point 2 is actually equals to specific volume at the point 3. How do I know that? Because once the piston was actually here at the state 2, right? So once the piston already reached at the stop here, it cannot go further, but then the temperatures will be dropped, but then the volume is going to be the same, because, you know, the piston is going to be remain at this point. You cannot get further even for the state number 3. So if you notice that for the state number 3 here, it's not going to be meaning that V3 is not going to be VG, see, because here is not going to be VG at 100 kilopascal, but then I have to use something like X something, see, but then I do know that my V3 is actually equals to V2. So once I found the V2 here, I can say that my V3 is something, and then I do know that my pressure P3 is actually equals to 100 kilopascal. Then I can find the information, whatever the information I want, because the tricks of using the steam table is actually you need to have minimum of 2 information. So let's say you have temperatures and pressure, then you can use the steam table. But then if let's say, okay, I want to find the V3 here, but then I only have one information, which is pressure equals to 100 kilopascal. I cannot really find the information for the V3 here. It can be anywhere. It can be here, 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 and etc. So I need to find another information. In this case, I'm going to state that my V3 is actually equals to V2. This one a little bit complicated, yeah. All right. So I'm going to move to this part, yeah. Second part of the question. This second part of the question should be very, very easy, because you only need to plug in the data givens. Alright, so I'm going to solve for this one, yeah. Determine the specific volume. Specific volume makes the question a little bit difficult, yeah. For the superheated water, because it was superheated water, therefore this one is just simply use table A6. Table A6, then you can find what is my specific volume for the pressure equals to 3.5 megapascal and temperatures of 450 degrees Celsius. This one is very, very easy. You can easily get, I don't know, 3 marks, I think, out of 10. Alright, for the ideal gas equation, this one is quite a surprise to me, because quite a lot of you didn't manage to get this one correct, even though you already done the experiment number 3, which is a perfect gas law. So let me start for this one. So for the perfect gas law, I do know that ideal gas equation, I have pressure multiplied by the volume equals to N number of moles multiplied by R U multiplied by T. So to define it, P is pressure. This one you should have learned during your secondary school, yeah, usually in the unit of kilopascal. And then I have a volume or isi padu in the unit of meter cubes, meter to power of 3, and then I have N number of moles, and then usually the unit of kilomole, and then RU here is universal gas constant with the unit of 8.314 kilojoule kilomole Kelvin, and then of course we have temperatures in the unit of Kelvin. As I said during the class, for us to have an equation over here, we have to make sure that the unit on both sides are the same. So let us check the unit. So for the pressure, I'm going to have the unit of kilopascal, multiply with the volume with the unit of meter cubes. And then on this right side, I'm going to have number of mole, which is kilomole, multiply with the universal gas constant with the unit of kilojoule over kilomole, multiplied by Kelvin, multiplied by temperatures, which is the unit of Kelvin. So now I'm going to cancel out some unit, because here kilojoule per kilomole, I'm going to have kilomole cancel out. Same goes for the Kelvin. So now I'm going to have the unit on the left side with the unit of kilopascal per meter cube. And then on the right side, I'm going to have the unit of kilojoule. Does it the same unit? So, actually it does mention here. See, the statement over here. In the table A1, the unit of kilojoule per Kelvin kilograms is equivalent to kilopascal meter cube kilogram Kelvin. So, means that I can say that my 1 kilojoule is actually equals to 1 kilopascal per meter cube. So this is what the statement means. So meaning that now I do know that my unit is going to be the same. I mean, the unit are correct, meaning that this equation are correct. Where does my gosh. Yeah, so I can say that because in the statement in the table A1, if you refer back to the table A1, it said that 1 kilojoule kilomole Kelvin are actually equals to 1 kilopascal meter cubes kilomole Kelvin. Because both sides are having kilomole per Kelvin, I can cancel out. So then I can say that 1 kilojoule, see, equals to 1 kilopascal per meter cube. So that this unit are actually correct. So that I can straight away plug in the unit. PV equals to NRU over T, NRUT. Yeah? So now I'm going to find the specific volume. I do know that the specific volume was actually equal to volume divided by mass. So now I have PV equals to N, number of mole, RU divided multiplied by T. And then I do know that number of mole is actually equals to mass divided by molar mass. And then the mass, usually the unit of M. Molar mass will be the unit of capital M. So now I'm going to plug the equation here into this one. So now I have PV equals to mass divided by molar mass multiplied by RU over T. And then I'm going to rearrange it. PV equals to M RU, universal gas constant, divided by M multiplied by T. But then I do know that PV equals to RU over M equals to R. How do I know? Because it does mention in the question in the table A1 here. Let me see it. See here, R, which is gas constant, equals to RU divided by M. So now I can also use this equation. PV equals to M R over T. But then I want a specific volume. Where does the specific volume is just equals to volume divided by mass. So now I have P volume. I'm going to move it to here, so it's going to be divide V over M equals to R over R multiplied by T. V over M is just specific volume. So specific volume equals to R multiplied by T divided by P. But then the temperatures is given, right, in the question. Yeah, the temperature is 450. So now I do know that the temperatures is 450 degrees Celsius, which need to be converted to Kelvin, which is 450 plus 273 equals to 723 Kelvin. And then the pressure here, it is a megapascal. So I don't want to use a megapascal, so I need to use a kilopascal. So 3.5. So here is going to be 3.5 times 10 to the power of 3 kilopascal. And then how about the R? R here is actually can be found from the table A1. See, for the R or the M is molar mass. So because they give me a water, so I need to find the R, which is gas constant, for the water, which is going to be 4615. So it's not that difficult, right? So here, my R here is going to be 0.4615 kilojoule, kilograms Kelvin. So see, that's why I converted from the pressure here from megapascal to kilopascal, because I do know that the kilojoule equals to kilopascal meter cube, something like that. So yeah, so this is how I solve for the ideal gas equation of state. Yeah, it is not difficult. First, we have to understand that ideal gas equation stated that PV equals to N RUT. Someone may ask, before this I did learn that during our secondary school, PV equals to N RT, right? But then the R here is not in, by definition, in this equation, R here is universal gas constant. But then we have a universal gas constant, RU, and also gas constant for specific substance, which is R. That's why they put it universal gas constant is going to be RU, and then gas constant for any specific component. For example, let's say I want to use air. The gas constant is going to be 0.2870 kilojoule kilogram Kelvin. Or I want to use, let's say, carbon dioxide. So now my gas constant is going to be 0.1899, and goes on. But then for all the component here, from here to here, the RU is going to be the same, which is equals to, you can refer to this table. See, RU for all component is going to be 8.314447 kilojoule kilomole Kelvin. So the R is different, but then the RU, universal gas constant, is going to be the same for all, but then the R is going to be slightly different. Alright, so now I'm going to move on to the last part of the question. Yeah, this one also should be straightforward, because you don't have to memorize all the formulas, right? Because you only have to use the formulas straight away. So for the van der Waals equation of state, this equation is given. So you should know that obviously the question here is not going to be for the ideal gas equation, but then this one is going to be for the van der Waals equation of state. Obviously, because we don't have any more. So here, the van der Waals equation of state, meaning that I need to find the specific volume, right? So now I have pressure multiply plus A over specific volume power of 2 multiplied by specific volume minus B equals to RT. So you should ask yourself which component is not what information we can obtain. Pressure is given in the question, 3.5 megapascal. So this one should be correct. And then this is what we're looking for, specific volume. Same goes for this one, which is what we're looking for. And then what else? The R here is just the same because it's using a water. Therefore R here, as I said before, 0. I cannot remember. 0.4615. So R here, where does it? Okay, R here 0.4615 kilojoule kilograms Kelvin, and then the temperatures here is also given 723 Kelvin. I need to use a unit of Kelvin. Yeah, so all the information given except for the specific volume, see, and also A and B. In order for me to apply this equation or this equation, I need to check which information is given. Pressure is given, R is given, T is given. The only unknown is specific volume here and here, and also A and B. So I need to find the value of A and also value of B before I can plug it into this equation. So I need to use this equation to find the value of A, and then this information to find the value of B. So let's try once. Yeah, I'm not going to try for both A and B, otherwise it's going to be very complicated and time consuming, and then this video is going to be like a, I don't know, end games movie, a long movie. All right, so now I'm going to try for this one. So now I do know that B equals to R TCR, critical temperatures, divided by 8 multiplied by PCR. So as I said before, I do know that my R is actually equals to 0.4615 from table A1. How about TCR and PCR? So I can also use the table TCR and PCR, which is from here. See, if you notice that here they stated that this is the critical point properties. So this is for temperatures, this one for pressure, meaning that this one is going to be TCR, critical temperatures, and then this one is going to be my PCR. So because they give me in the equation they use water, therefore I can use temperatures, critical temperatures of 647.1, and then the pressure of 22.06 megapascal. So I can say over here it's going to be very long. 0.4645 is going to be 647.1 divided by 8. PCR is actually equal to 22.06 megapascal. And as I said before, I don't want to use any megapascal, but I have to convert to kilopascal. You need to be consistent. 22.06 multiplied by 10 to the power of 3 Pascal. Why? Because 1 megapascal is actually equals to 1 times 10 to the power of mega, power of 6 Pascal. But then 10 to the power of 6 is actually equals to 1 times 10 to the power of 3 times 10 to the power of 3 Pascal. But then 1 times 10 to the power of 3 is kilo. Therefore, I can say that 1 times 10 to the power of 3 kilo Pascal is thus a unit conversion, which we already covered during our PCB subject during our first year. So this is how we solve for the question 1. It's not that difficult. Plus, if you notice that for the summary which I'm going to share with you, I only have something like 4 pages of note for the whole chapter, meaning that it's not that difficult for us. But then you have to understand, you cannot just simply memorize everything. But this one is involving an understanding on how to apply the information given in order for us to get the correct data. Thank you.